Today I wanted to talk about L'Hopital's rule, which is not necessarily something that we need to cover in class. You're not going to have any homework problems over it, but I think it's really helpful and it might be useful for you on the final exam. So what does L'Hopital's rule say? Well, it's named after a French guy whose last name is L'Hopital, spelled like this with the 2 dots over the O. But basically it says, if we're trying to find the limit as x goes to a of something that looks like f of x over g of x. We've done this before, right? And oftentimes when we take this limit, it gives us an indeterminate form, which more often than not, by indeterminate form, that means it's going to give us something like 0 divided by 0 or infinity divided by infinity. Okay, so if we're taking this limit and it gives us something that looks like this, what we can do is take the derivative of the top and take the derivative of the bottom, and then take the limit of that. Okay, so just to rephrase, the limit that we're trying to find is the same as the limit of the derivative of the top divided by the derivative of the bottom. And this greatly streamlines us solving indeterminate forms. If we remember back in the day, they would give us problems like find the limit as x goes to 3 of something like x squared minus 9 over x squared minus 5x plus 6. And of course, when we come to a problem like this, our first instinct is to plug in 3. We try plugging in 3. What do we get? Well, we have 3 squared minus 9 over 3 squared minus 5 times 3 plus 6. So this is 9 minus 9 over 9 minus 15 plus 6, which is 0 over 0. We have an indeterminate form. So that means we can apply L'Hopital's rule because we have this indeterminate form here when we try plugging in. And how do we apply L'Hopital's rule? Just to refresh, we're going to take the derivative of the top and the derivative of the bottom separately. So what that's going to look like for us is now we're going to take the limit as x goes to 3 of this derivative of the top here is just 2x, and then the derivative of the bottom here is 2x minus 5. And now we can plug in 3 to this. If we plug in 3 to this, we're going to get 6 over 6 minus 5 is 6 over 1 is 6. And so we could find this limit super quickly. Back in the day, the only technique that we knew how to do is we would take x squared minus 9 over x squared minus 5x plus 6, and we'd have to think about, like, how do we factor this? Does this factor into anything? Oh, we can factor the top as x plus 3 times x minus 3, and the bottom is x minus 3 times x minus 2, and we get cancellation like so. And then we can plug in 3, and we get 3 plus 3 over 3 minus 2 is 6 over 1, which you can still do. It's still an option, but for my money, I think L'Hopital's rule is a lot easier because especially factoring stuff like this can sometimes be hard, especially if you're in time pressure of a test. So let's take a look at some more L'Hopital's rules examples. Let's find the limit as x goes to 2 of x cubed minus 8 over x to the 4th plus 2x minus 20. Again, when we come to a limit like this, step 1, can we plug in 2? Is it that easy? Let's find out. If we plug in 2, we get 2 cubed minus 8 over 2 to the 4th plus 2 times 2 minus 20. So this is 8 minus 8 over 16 plus 4 minus 20, which is definitely 0 over 0. So we have an indeterminate form. And that means we can use L'Hopital's rule again. So we just have to take a derivative of the top and the bottom. And that means we have the limit as x goes to 2 of 3x squared over 4x cubed plus 2. We can plug in 2 to this. We get 3 times 2 squared over 4 times 2 cubed plus 2, which is 3 times 4 over 4 times 8 plus 2, which is 12 over 35. And we're done. We found the limit. Easy peasy. One step. Could you imagine trying to factor this and seeing if you get any cancellation? It sounds awful. Okay, let's take a look at some more examples. With trig this time. We're trying to find the limit as x goes to pi over 2 of cosine squared x divided by 1 minus sine of x. Again, if we try plugging in pi over 2, what do we get? We have cosine squared pi over 2 over 1 minus sine pi over 2. Cosine of pi over 2 is 0, because pi over 2 is the straight vertical line upwards. So we get 0 squared over 1 minus, and then sine of pi over 2 is vertical line upwards, so it's 1. And so we get 0 over 0. And that means we can apply L'Hopital's rule again. So this gives us the limit as x goes to pi over 2 of the derivative of the top. So let me change colors here, and we'll take a look at the derivative with respect to x of cosine squared of x. Remember, cosine squared of x, it's typically easier to write this as cosine of x squared. We have a function raised to a power. That means when we take the derivative, we get 2 cosine of x times the derivative of the inside, which is minus sine x. So we get minus 2 cosine x sine x. So that's our top. And then what's the derivative of this bottom? 1 minus sine x. When we take the derivative, we're going to get 0 minus cosine x. So I'll just erase this 0 because it doesn't really do anything. And now we get some nice cancellation. The negatives on top and bottom cancel out, the cosine cancels out. And so what we're getting is the limit as x goes to pi over 2 of 2 times sine of x. We can plug in pi over 2. We get 2 sine pi over 2, which is 2 times 1, which is 2. So even though this function, cosine squared x over 1 minus sine x, gives us this indeterminate form when we take the limit, we can take derivatives of the top and bottom, take the limit of that, we find the limit relatively straightforwardly. Okay, sometimes it's not enough to do L'Hopital's rule once. Sometimes you have to do it twice, even 3 or 4 times. Let's see an example where that might happen. Okay, so if we want to take the limit of this function here, again, if we try plugging in 0, you'll find that we get an indeterminate form. We get 1 minus 1 on top, we get 1 minus 1 on bottom, we get 0 over 0. So we can apply L'Hopital's rule, which means we take the derivative of the top, the derivative of e to the x minus 1, gives us e to the x minus 1. And the derivative of the bottom is going to give us minus sine x. And now we can try plugging in x equals 0. We get e to the 0 minus 1 over minus sine 0. That's 1 minus 1 over 0, which is 0 over 0. And we are indeterminate yet again. But because we are in a 0 over 0 form, that means we can apply L'Hopital's rule again. We can take the derivative of the top and bottom again. The derivative of the top here is just e to the x, and the derivative of the bottom is going to give us minus cosine x. We can plug in 0. We get e to the 0 over minus cosine 0. This gives us 1 over minus 1, which is a negative 1. So we apply L'Hopital's rule more than once. We keep getting these indeterminate forms. That means we can keep applying L'Hopital's rule, and we find our limit. One cool thing about L'Hopital's rule is we can also use it for infinity over infinity. Right? Previously, we've been seeing 0 over 0. We can also use it for this infinity over infinity. We have other methods for finding horizontal asymptotes like this, behavior as x goes to infinity. But this is another kind of more straightforward way to do it. If we try and plug in infinity here, we're going to get infinity on top, infinity on the bottom. So we can apply L'Hopital's rule. Let me switch to my pencil. We can take the limit as x goes to infinity of 6x plus 9 over 14x. Again, this gives us an infinity over infinity error. So we can apply L'Hopital's rule again. We get the limit as x goes to infinity of 6 over 14, which is just 6 over 14. And we can reduce that. Both of those are divisible by 2. So we get 3 over 7. Okay, and one more example with, as x goes to infinity. Here, as x goes to infinity, e to the x also blows up to infinity, and x cubed also, of course, blows up to infinity. So we can apply L'Hopital's rule, take the derivative of the top and the derivative of the bottom. Both of these, of course, blow up to infinity, e to the x and 3x squared. So we can apply L'Hopital's rule again. And we get this. But both of these, again, blow up to infinity. So we can take L'Hopital's rule again of e to the x over 6. We get this. And now this is not an indeterminate form. As x gets really big, this top part here continues to grow to infinity. The bottom part is a constant. And so that means the limit is infinity. Okay, we just keep applying L'Hopital's rule, and we find this limit is infinity. And note, there's nothing special about this cubed here. In fact, if p of x is a polynomial, then the limit as x goes to infinity of e to the x over p to the x is infinity. And one way you can see that is that e to the x grows way faster than any polynomial ever can. If you go into like Desmos and you graph e to the x and then pick your favorite polynomial, even if it's something like x to the 250th power, some really large exponent, e to the x, if x gets big enough, it grows way faster than x to the 250th. But anyway, that is L'Hopital's rule. This is just a little side note that I think y'all might find helpful. Thank you very much.